Hi, everyone. So today's video is kicking off Chapter 7. Chapter 7 is a lot packed into one. We've got work, springs, kinetic energy, and power all in one chapter that we're going to try and get through. So first, let's talk about how a scientist defines work. We've got a couple examples here, right? We've got some workouts to put this into perspective for you, if you've ever done these workouts before. So physics work is a little different than the word that we just use colloquially, saying, work sometimes goes hand in hand with effort. That's not the case in physics. So we'll look at number one here. In which workouts does the system do physics work, right? So first, let's say a coach says to hold a wall sit for 5 minutes. If you guys have ever done a wall sit, 5 minutes is quite a long time unless you're an athlete. However, that is not work if you ask a physicist. Holding a wall sit takes a lot of effort and a lot of strength, but it is not work. Next, do a burpee. If you don't know what a burpee is, it's when you are standing, get down on the floor, do a push-up, then jump up and do a jumping jack real quick, and you do a bunch of those all over and over and over and over and over again. Sometimes instead of doing a jumping jack, you just jump as high as you can. Burpee also is not physics work. We'll talk about what this definition is doing to get rid of all of these things all at once. But doing 50 burpees, that's a ton of burpees. Doing a wall sit for 5 minutes, that's a long time to do a wall sit. All of these take a lot of effort, but it's not actually work when we talk about physics. Next, we lift a chair off the ground. Okay, lifting a chair off the ground is something pretty easy that we can all do in class, as long as your chair isn't connected to a desk, right? But that one, that is work. Okay, lifting a chair off the ground would count as work. Now, your coach is going to tell you to hold that chair above your head either until the coach leaves or until you die of exhaustion, which is a common hyperbole that can come from coaches, right? So if you hold that chair above your head without it moving, right, you're just holding it there, that is, again, not work. Okay? None of those are work. The only one that is work is lifting the chair off the ground. Now, what is the exception here, right? What does the chair lifting off the ground have to do with, how is that separate from everything else? Well, the chair lifting off the ground, it starts in one place and it ends in a new place, right? That is the difference here. When you do a wall sit for 5 minutes, you're not going anywhere. So that in physics doesn't take work. If you do a burpee, right, you get down, do a push-up, jump up, do a jumping jack real quick, and now that you're done, you have gone nowhere. You've done all of that effort to go right back to where you started. No effort. Sorry, not a lot of effort, no work. Next, we lift a chair off the ground. That starts on the ground, and then you lifted it up off the ground. It moved. That was work, right? Then D, finally, we hold the chair above our head, right? If you do it properly, chair's not going to move. So again, you did no work. The key here is displacement. So let's talk about that. Okay. Number two, what are the two ingredients for physics work? So the two ingredients that we have here, okay, they are force and displacement. And we'll talk about displacement. What is displacement and how is that different than distance? So let's say you run a 5K. Okay. You start here, you run out and around, up here, go all the way out here. Okay, you start and finish right there at the same point. If you ask physics, you did no work because you put all that effort to go nowhere, right? You started and finished at the same point. So running that specific course in a 5K took no work if you look at your displacement, right? Because your position hasn't changed from start to finish. Now, we can say Now let's stretch out that course, right? Now it's a 5K course from start to finish. Now you have gone 5 kilometers, right? So then that would be a 5K, right? But it's all about displacement, not distance. It doesn't matter about distance, it matters about displacement. For example, we have talked about circular motion, right? Circular motion has displacement and distance involved, right? This arc, delta S, that is your distance, right? But your displacement would be here. That would be your delta R. That is displacement. Okay? Displacement just cares about the difference between point A and point B. It doesn't matter the path you took. It just matters what is the difference between point A to point B in a straight line. So that's what we're going to use for work, right? Oops. Now, how many forces do work in the chair, on the chair in scenario C above? So let's get a free body diagram. Okay, we've got chair, right? You've got the applied force, right? And then you've got mg, okay? So you've got two forces working on this chair, okay? The applied force in scenario C, right? We are lifting the chair off the ground. This is doing positive work. When I write work, I put those lines at the top of my W just because my penmanship is crap. And I want to make sure that that is work, not some other omega or whatever. Now that force applied is doing positive work, right? It is moving that chair in the positive direction. Now mg is actually doing negative work in this scenario because it is resisting the displacement, right? So the applied force is doing positive work. The gravity is doing negative work. Now, number 4 asks, what was the net work in scenario D? If you remember, scenario D is that we hold the chair in place. Oops, I need my eraser. Go, eraser. So if we look at the scenario D, right? Scenario D actually has the exact same free body diagram, right? You've got force up, mg down, but now it's going nowhere. That means that your net work is going to be 0, right? A sign of having real net work, okay? If you want net work, you need displacement. If it's going nowhere, there will be no work done, right? So here we have the same free body diagram, same forces, it's just not moving. So here we have a net work of 0, whereas before in scenario C, lifting the chair off the ground, we have a net positive force. Now, number 5, okay, it says, consider the air turbine pictured. So we've got a picture of a turbine up here on the slide, okay? Now it says, is the work done by wind on the wind turbine an energy transfer? So we've got this wind turbine, okay? And the turbine blades, okay, they go in a circle. Now, if you look at that system as a whole, right, as the wind, say the turbine is sitting still, blades aren't moving. The wind blows on the turbine, now the blades start moving in a circle, right? So that is obviously an energy transfer, right? It starts with no motion, then all of a sudden it is moving. That's an introduction of kinetic energy. Then the turbine actually converts that kinetic energy into electrical energy. There is a big energy transfer there, right? That's huge. It's actually really important to many societies around the world. But if we look at how much work is done in that turbine, right? If we back out and just look as a system, that turbine is moving in a circle, okay? Those blades, unless we stop and look instantaneously, right, from the blade moving around its path, if we look at it as a system, there's no work done, right? Because it is just a cycle, right? All of that energy is not moving the turbine anywhere, right? Yes, the blades go in a circle, but the turbine's staying still, hopefully, right? If it starts moving, we need to tell somebody. But that is an energy transfer, but there's technically no net work because there is no displacement, unless you want to look in instantaneous scenarios where the blade moves in its path. Then we can look at, okay, it moved from here to here. That took some work here to here. That took some work here to here. That took some work. But if you add all of that up, it's going to equal 0 because there will be no net work. Now, our last question, number 6, scientists defining work. Is it wise to define energy as the capacity to do work? And I would argue, no, that is not a good definition of energy. It's a common definition of energy that we use as science teachers, but it's a very broad definition. And as a broad definition, it has its merits. But here, energy is not just the capacity to do work, right? Not all energy is going to do work. For example, heat energy, thermal energy, that just radiates. That does no work. Energy cycles such as this wind turbine, right? It's stationary, wind blows, okay, that converts, that transfers kinetic energy to the turbine, and the turbine takes that kinetic energy, makes it electrical energy, but when the wind stops, the turbine stops moving again, so then it's just an energy cycle, right? There's no total work done, right? As a system, no network. So these do no work, right? Energy, as on a broad definition, the capacity to do work is not great when we look at specific circumstances, right? So we won't use that definition of energy as we continue going forward. Okay, now 7.2. Okay, we're going to look at method 1. This is the equation F delta R cosine theta, or you can call it FD cosine theta. Okay, because that delta R is going to stand for displacement. Okay, so let's look at letter A first. Which forces do work in this scenario, in this case? So here we have a large mg. Here we can see that the vertical component of this pull force, okay, is helping that normal force balance mg. Okay, so mg is balanced between the normal and the pulling force. But the pulling force is also pulling to the side, and we have this displacement vector shown here to tell us what direction that displacement is taking place. So for an object to do work, okay, we have to have the force going in the same direction as the displacement. So here, normal and mg, they're perpendicular to the displacement. That means that they're not going to do any work because they aren't contributing in that direction, right? However, if we look at F, okay, F cosine theta, which is this length here, okay, that is going to actually do work because it is contributing in the displacement direction. Now, if we look at F sine theta, okay, so here's F sine theta, that is not going to contribute to the displacement. So F sine theta doesn't help, but F cosine theta is the one doing the work in this scenario, right? So when we look at this equation, F delta R cosine theta, this theta is a very special theta. It's not something that we can move around like in our previous problems where we can manipulate theta to say, well, this is the theta in the horizontal. Let's find theta in the vertical. This is a specific theta. This theta is specifically the angle between your force and the displacement. It's specific because if it wasn't, that angle could be anything, and that's going to throw off your work calculation entirely, right? So that theta is between whatever force you're calculating and the displacement vector. What is the angle between those two vectors? All right, let's move on to letter B. Okay? Letter B asks to calculate the work done on the vacuum. So we can look at this. We'll solve it in terms of delta R because we don't know how far the vacuum is moving, right? But we have this. It's actually the exact same free body diagram. So we can see that the summation of forces in the X really just equal F cosine theta. So we've got F cosine theta. To find work, right, you take whatever force you're trying to find, right, the magnitude of the force times delta R times cosine theta. Well, here, F cosine theta is already accounted for because here the force we need is F cosine theta, right? So if we wanted to find this, right, we would take the force, which is 50 newtons, times delta R times cosine of 30 degrees. Okay. Now, the force that we're looking at, F cosine theta, right, that is the force in the X direction. But work doesn't care that there is that cosine theta there. Work just asks, what's your force? What's your displacement? What's the theta? So the force is 50. The displacement, we don't know. Then we have cosine 30, right? So your answer would be 50 cosine 30 times delta R. And then you can break down cosine 30. That's square root 3 over 2, I think. So then you could say that that would be 25 square root 3 times times delta R. That will work also, right? But we don't have dr. We don't have delta R. So that's how you can calculate the work done on the vacuum. You don't take F cosine theta twice, right? So we wouldn't say that this is 50 cosine 30 delta R cosine theta. Okay? You wouldn't do that because work just cares about what is the magnitude of that force. Okay? We just want to know how strong is the force you're worried about. Don't worry about the angle with respect to the X or the Y axis. Cosine theta, this special theta, actually takes care of that. Because remember, theta is the angle between F and delta R. So that cosine theta is going to take care of the rest of it. So this is just 50. Okay. That's all you would worry about on that one. All right, next. What are the various units for work? So work has several units that we will use in this class for AP Physics, and some that we will not use for AP Physics. So, for example, we've got Newton meters, right? You've got force times displacement, Newton meter. That one we will use. You have joules. Joules, we will use that one, right? Another one is a Pascal meter cubed. Okay, that one we will not use. That has to do with pressure, right? Pascal is a unit of pressure. It's Newton per square meter. Next, we have a Coulomb volt. That we will not use. That is used in E&M. That's not something we're going to worry about. The last one is a watt second. Okay, that's watts. Okay. Watt seconds. That one is also usable because when you're talking in relation to power, watt second is an acceptable unit. Now, the ones that we should focus on are Newton meters and joules. I have the custom of using Newton meters for work and joules for energy because my students in the past and future students, it's very easy to get things confused when you use the same unit for different ideas, right? So when we use energy, we will use joules. When we use work, I will use Newton meters just to show that these are separate. But if I slip up and put a joule for work or a Newton meter for energy, forgive me, they're the same thing. All right, next we have work depends on the angle between force and displacement. So here the force in the is the same in each situation, right? We've got situation A, B, C, and D. We want to rank the situations from most positive to most negative. So if we look at work equals F delta R cosine theta, okay, when you take the cosine of theta, it's going to be somewhere between 0 and 1, right? It can never be less than 0 or greater than 1, unless we're talking about negatives, which we will here. But we want that cosine, if we want it the most positive it can get is 1. So that would be if we had cosine 0, which would be C. Okay, that is number 1. Then after that, if we had cosine 0, or sorry, if we had cosine 90, that would equal 0. So if we go from positive to 0, that would be here, A, number 2. Okay. The others are pointing actually in the opposite direction, which will give you negative work. So in letter C, you've got the force and the displacement going in the same direction. In letter A, the force is perpendicular to the displacement, giving you 90 degrees. Cosine of 90 is 0. It's also, if you want to think about it in the terms of axes, force and displacement are not going to interact, right? Nothing in the x can affect the y. So force will not contribute to the displacement at all. Now in letter D, that is some angle greater than 90 degrees, and if you have a cosine somewhere between 90 and 180, that's going to give you a negative number, right? So letter D is going to be third in our ranking from most positive to most negative, because B is a perfect 180. Cosine of 180 is negative 1. So that is perfectly most negative, right? Just how number 1 is perfectly most positive. Number 2, letter A, is perfectly 0, and 3 is somewhere in the middle. All right, now we've got this practice problem. Okay, a truck is dragging a stalled car up a 20-degree incline. Okay. Say that is 20 degrees. The force in the tow line as the car is dragged up the curve or up the incline is 1,600 newtons, right? And that tow line is at an angle of 30 degrees with the road. How much work is done by the truck on the car in pulling it 0.5 kilometers up the incline? So say we have this car, and then we have this angle 30 degrees for the tow line. Okay, that is our force that's pulling us. Now, if we want the work, it asks specifically work done by the truck on the car. Okay? So that is specifically just this force. Okay? That force has a strength of 1,600 newtons. Okay? We don't bother with F cosine theta or anything, or F in the x direction. We just care about how strong is the strength, or how strong is the force, 1,600 newtons. Then the displacement. Okay? Displacement is 0.5 kilometers. We'll call that 500 meters. Okay? And that is along the incline. Okay? That is our delta R vector. Now we want to look at the angle between the two. Well, we've got 20, 30, sometimes kids want to shoot for 50 degrees, but we just want the angle between the force vector and the displacement vector, and that is 30 degrees, as we can see right here. So then you would take all of that, cosine 30 degrees, and this will give you a full answer of 690,000 Newton meters. Oh, whoops, lost my slide. 690,000 Newton meters. So that's how you could find the work done by a certain force. As we get on further into this unit, we'll actually do a work done by several forces, and we'll find summation of work. But that's for another time. So this is how you can find work using that FR cosine theta. Now Sometimes this FD or FR, right, goes hand in hand. Sometimes FD cosine theta does not always work. So why does FD cosine theta fail in these cases? Okay, so we've got these two graphs, right? Even if we did know the theta, okay, say theta is 0 degrees, the force is perfectly along the displacement. What is the issue here? Why could we not find the work? Well, this is very similar to our general kinematics rule. General kinematics relies on the rule that acceleration must be constant, right? If the acceleration changes across that time period, it doesn't really work. We can't use general kinematic equations, and we can't use those graphs, right? However, if we use calculus, it can work, right? So here is the same thing. Here, our force is actually changing as it moves this object along the displacement, which is an issue. FD cosine theta doesn't account for F possibly changing as the object moves. Okay? So when we have a graph that shows this case, there are two things that we can do, right? Which is what it asks below. Okay, what are two alternatives to find work in these cases? So on this one here, this would be much easier to find work. Here, if you find the area under this curve, okay, you've got really easy finding that area. Here you've got 5 times 4. Here you've got 1/2 times 2 times 5. You've got the area of a square, or I guess that's the area of a rectangle, the area of a triangle, and you can get that area, right? That would then just be 20. Here you've got 5. So then the total work done here is 25 Newton meters. So you can do the area under the curve if it's nice and geometric, right? Sometimes not so geometric. So here, what you want to do is you want to take the integral. Okay? Here you would take the integral of your f of x with respect to x, and that equals work. So those are your two options, area under the curve or integrate. So let's give this a shot. Okay, let's put calculus to work. So the force acting on a particle follows the function given to us right there. Okay, we have 5x squared plus 2x plus 10 newtons. Okay, that is our f of x. Got 5x squared plus 2x plus 10 newtons. Okay. Now, letter A asks determine the equation for work. Then letter B asks calculate the work done from the position 7 meters to the position 12 meters. Then letter C asks how much work is done if you go the opposite direction from 12 meters to 7 meters. And then we'll answer D later. So first, letter A. Okay. A. It wants to know the equation for work. So what we'll do is we will integrate f of x dx. Okay. So to do that, we will integrate 5x squared plus 2x plus 10 dx. And this would give us 5/3 x cubed plus 2x squared over 2, so that's just x squared, plus 10x, then plus a constant c. Right? That is our equation for work. Now it asks calculate the work done from the 7 meter mark to the 12 meter mark. So here we would take, let's see, so this is letter B. So then we would find work. That would be the integral from 7 to 12 of your f of x dx. Okay, we already have that equation. Okay, so you can just take work, okay, from 7 to 12. So let's do that right here. We have 5/3 times 12 cubed plus 12 squared plus 10 times 12. Okay. then you will subtract your initials, right? Then you subtract 5/3 times 7 cubed. Then you'll subtract 7 squared. Then you subtract 10 times 7. Okay? And if you do all of that, you should get 2,450 Newton meters. Okay? Put that all in your calculator, that's what you'll get. Now, letter C asks how much work is done going the opposite direction from 12 to 7. So let's look at letter C. Letter C asks us to find work from 12 to 7. Okay? So if we want the integral of 12 to 7 of f of x dx, this equals the negative integral from 7 to 12 of f of x dx. Now you can go through and do the work if you'd like to prove that this is true. But we know that the work from 12 to 7 is going to be negative 2,450 Newton meters because of this nice little integral rule. Okay, the integral, if you take the integral backwards, instead of from 7 to 12, you go from 12 to 7, it is just the negative integral of that same thing flipped. If you flip, go from forward to backward or backward to forward, just multiply by -1 and you'll have the exact same value. All right, now our last talking point, okay, letter D. So does positive area under a graph always mean work is positive? So if we look right here, okay, let's say this delta x goes from 7 to 12. Okay, that is a positive area, right? Positive area. But if you read the graph backwards, you're going to flip the sign. Okay, it's going to have the same value, but you flip the sign. And this is going to happen often in this chapter. If you read the math from left to right, like normal, then positive area means positive work. However, if you read it backwards, positive area means negative work. So positive area can't always mean positive because sometimes you have to read your math backwards. Sometimes that's necessary. All right, so this is the end of our first video on work. This is our work methods 1. We did a little bit of the no-calc method, and then we did a little bit of the calculus method. And in our next video, we'll go over work methods number 2. We'll talk about the scalar product.